This is our first video for Chapter 13, which is all about solutions. In this chapter, we're going to need to be able to calculate concentration, and so in this video, we're going to practice our concentration calculations. Now, just a little review about what it means to make a solution. A solution is always made out of at least one solute and a solvent. The solute is what there is less of. The solvent is what there is more of. And the most common type of solution is something like what we see here, where we're taking a solid and we are adding it to a liquid. The solid would be the solute, something that there is less of. The solvent would be the liquid, something that there is more of. Now, when you mix those things together, you get a solution. And here, since we can't tell the difference between the components when they've been mixed together, it makes a homogeneous mixture. This is a good time to review heterogeneous and homogeneous, those words that we use to describe matter that we learned in Chapter 1. Now, when we want to describe how much of the solute is in the solvent, we can use some units of concentration, and some pretty common ones are ones like percent by mass and molarity. These ones in the middle, percent by volume and mass, volume, percent, those are less common, but they are valid units of concentration. In this video, we're going to talk about all these types of concentration. Some of them you might already know how to calculate, but we're going to review them anyways. You might know mass percent. You might have done mole fraction when you did gas laws, and you've probably calculated molarity. But we're going to go through each one of these and do a practice calculation. The first one that we're going to do is molarity. Molarity is the most common type of concentration that's used by chemists, and molarity means the moles of solute divided by the liters of solution. So here's a practice problem. It says that we have 0.175 grams of ammonium acetate, and it's dissolved in water to make 45 milliliters of solution. What's the molarity? When I think about a problem like this, I'm going to use my problem-solving technique if I'm just going to give myself a goal at the end. I'm trying to calculate molarity. And molarity is moles of the solute divided by liters of solution. And then I'm going to look at my problem and figure out how I can get to these units and how I can calculate molarity. When I read back over the problem, it says that I have 45 milliliters of solution. So I can pretty easily get from milliliters to liters. And then to find my moles of the solute, it tells me that I have 0.175 grams of ammonium acetate. That's what I'm going to use. That's what there's less of, so that's the solute, and I'm going to use that to find the moles of the solute. So what I've done is I've just written the information, the numbers from the problem on the slide before. And what I'm going to do is I'm going to first calculate moles, and then I'm going to calculate liters, and then I'm going to put those two together to find molarity. Okay. And the first step was to calculate moles. In the problem, it tells me that I have 0.175 grams of ammonium acetate. So we're going to need to use our nomenclature skills here to figure out what the formula for ammonium acetate is, and then we can find its molar mass. Remember, the ammonium ion is NH4, acetate, looks like that. They go together in a 1-to-1 ratio. And if you calculate the molar mass, so you add up a nitrogen, 4 hydrogens, 2 carbons, another 3 hydrogens, and 2 oxygens, you will get a molar mass of 77.01 grams per mole. So I can convert to moles by using my molar mass. And when I do that, so the grams cancel out with grams and I get moles, I get 0.002272, there are a lot of numbers after that, moles of ammonium acetate. And I'm going to mark my sig figs. This only had 3 sig figs, so I'm going to mark this. This is 1, 2. I'm going to mark it to 3 sig figs. All right, so I have converted grams to moles. Now I need to convert my milliliters to liters because I need liters on the bottom. And I have 45 milliliters. I know that there are 1,000 milliliters in 1 liter. So it's 0.045 liters. And it only had 2 sig figs, so I'm going to make sure I mark that to 2 sig figs. Now I have my moles and my liters. I'm going to bring them down. So this was 0.02272 moles divided by 0.045 liters. And when I do that, I get 0.05049 molarity. With sig figs, this had 3, this had 2, this should only have 2. And so I get 0.050 molarity. Now that we've calculated a concentration that you've probably been familiar with, molarity, I want to introduce one that you might not have heard before. This new one is called molality. It's very similar spelling than molarity, and it's easy to get them confused. We have different symbols for molarity and molality. Molarity is a capital M, and it's moles of solute divided by liters of solution. But molality is this little fancy M. It's usually kind of an M that looks like that. And it's related, but not exactly the same. So what's on the top are the same. Moles of solute and moles of solute are the same. But what's on the bottoms are different. For molarity, it's liters of solution. And for molality, it's kilograms of solution. So let's do a little practice calculating molality. And here's our practice problem. The problem says that we have 1.5 times 10 to the 3 milliliters of water that's added to 0.2 pounds of magnesium sulfate. What is the molality? So again, I'm going to use an equation to help me get started. I'm trying to find molality, so I know that's the moles of the solute divided by kilograms of solvent. And so in this problem, the solute is what there's less of. That's going to be our magnesium sulfate. And the solvent is what there is more of. That's going to be our water. So maybe a better way to write this would be moles of magnesium sulfate divided by kilograms of water. And when I do that, I can see that I can use my 0.2 pounds of magnesium sulfate to find moles, and then I can use my milliliters of water to find kilograms of water. So my first step is to find the moles of magnesium sulfate. I have 0.2 pounds, and my problem tells me that 1 pound is 453.59 grams. And then I need to get from grams to moles. And to do that, I need to be able to use the molar mass. To find the molar mass, I need to know the formula for magnesium sulfate. And so just a little reminder, magnesium is in the second column, so it's 2 plus. Sulfate is SO4 2 minus. Because their charges are the same, they go together in a 1-to-1 ratio, and we just get magnesium sulfate. And when you add up a magnesium, a sulfur, and 4 oxygens, you get 120.37 grams per mole. So that's what I'm going to put in for my molar mass. And when I do that calculation, pounds cancel out with pounds, grams with grams, and I just get moles. And the number that I get is 0.7536 moles. Now it only had 1 sig fig. That's unfortunate, but I'm just going to mark this to 1 sig fig. So I've gotten my moles of solute done, but I need to find my kilograms of solvent, and that's my water. So I'm going to use the information about my water here. And so there's 1.5 times 10 to the 3 milliliters, and I need to get to kilograms. I need to get to a mass. The problem told me that the density of water is this. So 1 milliliter is 0.998 grams. And I can get from grams to kilograms. It's 1,000 grams in 1 kilogram. So units cancel out. I get kilograms. And the number that I got was 1.497 kilograms. Now a sig figs has had 2, so I'm going to underline to 2 sig figs there. Now I have my moles, and I can divide them by my kilograms. When I do that, I get a molality of 0.503, and so I'm going to label it molality, the fancy M there. Now remember, with 1 sig figs, our moles only had 1 sig fig, our kilograms had 2, this only has 1, so that's going to be 0.5 molality. Now I just wanted to pause for a second, and I wanted to kind of compare and contrast molarity and molality. Molarity is moles of the solute divided by liters of solution. Molality is the same on top, moles of solute, but kilograms of solvent on the bottom. Now there's a couple reasons why you might not have heard of molality. The first one is that molality is mostly only used for colligative properties calculations, which we are going to do in chapter 13, but we haven't needed to do until then. So it's really just focused, it's kind of only appropriate for colligative property calculations. The other reason why you might not have heard of molality is because the molality and the molarity, the numbers for a solution. So if you calculate molality and you calculate molarity, they're almost always exactly the same or very close to each other. And the reason why that is true is because when you look at what's different between them, liters of solution on the bottom for molarity and kilograms of solvent on the bottom, those look like totally different numbers. But if you think about the solutions that we've made, the solutions that we make are usually water being the solvent. And water has a density of about 1 gram per milliliter. So 1 liter of water is equal to 1 kilogram, about equal to 1 kilogram of water. So if you're making your solutions with water, which we are most of the time, and you're at about room temperature, which we are most of the time, 1 kilogram of solvent, 1 kilogram of water is going to equal 1 liter of water. So these numbers come out to be very close to each other almost all the time, as long as your solvent is water, as long as you're at about room temperature, and as long as the concentrations are relatively low. Once you start getting to pretty high concentrations, like, over 2 molarity or something like that, as the concentrations start to get higher, these numbers start to differ more and more. So another reason why you haven't heard about molality is that it's almost always the same as molarity for the solutions we've seen up into this point. But once they don't have to be the same, and if we start working with higher concentrations or solvents that aren't water, these numbers could be different from each other. So let's talk about weight percent. Weight percent is defined as the mass of the part on the top and the total mass on the bottom. You can also think about this as being, so the mass percent, that's the same thing as the weight percent. The mass percent is the mass of the solute on the top, and the mass of the solute plus the mass of the solution, mass of the solvent on the bottom, times 100%. And that's the same thing as the mass of the solute divided by the mass of the solution times 100%. Because remember, a solution is always made up of a solute and a solvent. So let's get a little bit of practice. In this problem, it says that we have 1.1 kilograms of glycol as an antifreeze to 3 kilograms of water. What is the mass percent? And again, mass percent, I'm going to use an equation to get me started. It's going to be the mass of the solute, that's what there is less of, divided by the mass of the solute plus mass of the solvent on the bottom, times 100%. And just a little reminder, when we see the word percent, cent means 100. So that means that we are multiplying it by 100. So anything with a percent, we always multiply by 100. So now I need to identify what the solute is and what the solvent is. The solute is what there is less of. So there is 1.1 kilograms of glycol, that's less. And my solvent is what there is more of. There are 3 kilograms of water. So I'm going to say the water is my solvent. So I'm going to put my 1.1 kilograms of glycol on the top. And I'm also going to put that on the bottom because it's part of the solution. But I also need to add in my kilograms of solvent, and that is water times 100%. And a little plug for sig figs when we're doing addition here. If I have 3 and I add 1.1, I get 4.1, but this is to the ones place, and that means this can only be to the ones place. So I actually get a 1 sig fig number out of that. That's a little bit unfortunate. So basically it comes out to be 1.1 kilograms on the top and 4.1 kilograms on the bottom. Now when I do the division, I have 2 sig figs on the top and 1 sig fig on the bottom, which means that on my calculator I get 26.829 mass percent, but it should only have 1 sig fig, and that means 30% mass to mass. We hate rounding that much, but we only had 1 sig fig here. Now, just a little reminder, mass percent is the same thing as the weight percent. And when we were doing percent, we multiplied it by 100. I want to figure out how to do per million. So that's the next calculation that we're going to practice. It's very similar to percent, but so percent means we multiply it by 100. In per million, it just means we multiply it by 1,000,000. So the number on the top is the same, the number on the bottom is the same. The only thing that we're changing is what we multiply it by. So let's think about the same problem again with the same numbers. And we got our percent by taking our solute and dividing it by the total mass of the solute and solvent together to make the solution times 100%. And we found out with sig figs, it came out to be 30%. We're going to do the same thing. We're just going to multiply it by 1,000,000 now. So times 1,000,000. And when we do that, we get 300,000 parts per million. So that symbol there, ppm, just means part per million. You could also do this calculation. So this was our answer. But if the question asked for parts per billion, we would just multiply our solute divided by our solution. We would multiply it by 1 billion here. And so we would multiply it by that. So that's what we would put there if it were parts per billion. Let's practice our parts per million calculation by doing this one. This problem says that the EPA, so that's the Environmental Protection Agency, its regulations set the concentration limit for copper ions in drinking water at 1.3 parts per million. A 500 milliliter bottle of water is found to contain 0.8 grams of copper. Is it safe to drink based on the EPA standard? So what we're going to do is we're going to calculate the parts per million in the bottle, and then we're going to compare that to what the EPA says it's safe. If it's above 1.3, it's not safe to drink that water. If it's below 1.3, then it's going to be okay. Right, so to calculate parts per million, we're going to need to know grams of copper ions on the top, so that's our solute, and we're going to need to know grams of solution on the bottom times 1,000,000. Now that's the same thing as grams of copper ion divided by grams of copper ion plus grams of water, because those two things make up the solution. So times 1,000,000. So I need to do a few calculations. First, I need to go from my 0.8 milligrams of copper, and I need to get grams of copper. And then I also need to take my 500 milliliters of water and find grams of water. The problem tells me the density, so I should be able to do that. I'm going to do those one at a time. So I'm going to do my grams of copper first. I have 0.8 milligrams of copper. I know that there are 1,000 milligrams in 1 gram. So that's 8.0 times 10 to the negative 4 grams of copper. To find my grams of water, I'm going to start off with my 500 milliliters of water. I can use the density. It said that 1 milliliter is 0.998 grams. And so when I do that, I get 499.0 grams of water. And now I'm going to put those two things. So I'm going to put my grams of copper there, and grams of copper there. And then I'm going to take my grams of water and put it right there. All right, so parts per million equals times a million. That, and I got for parts per million 1.6 parts per million. And when I compare that 1.6 to the 1.3 that's safe to drink, it's higher than the 1.3, so I would say that that is not safe. So let's move on to another type of calculation for concentration, and that's mole fraction. The mole fraction is the moles of the part divided by the total moles. And when we say mole fraction, if we have a mixture of, like we had before, copper ions and water, we would have a mole fraction of copper and we would have a mole fraction of water, and they always, all the mole fractions always add up to be 1. So that's what this is saying right here, is that all the mole fractions always add up to be 1. Now why that's helpful is if you calculate one and you want to find the other, you can just subtract from one to find the other one. Now again, the mole fraction, so if I was trying to find a mole fraction of copper ions, it would be moles of copper divided by moles of copper plus moles of water. Okay, so it's kind of like a percentage of moles, except for you're not multiplying it by any percent. It's going to be like a percent of moles in decimal form. Let's practice this calculation by kind of wrapping these things together. Here's a problem that says a solution is 20% sulfuric acid by mass. So that's a mass percent. It has a density of 0.120 grams per milliliter. Calculate the concentration of the sulfuric acid in these units. So we have 3 different calculations. We'll just kind of go through. We've already practiced molarity and molality, so we'll do those first, and then we'll finish it up with the mole fraction. So I've taken the information and I've put it up here on top so that we can keep track. And the first calculation that we're going to do is molarity. Molarity is moles of sulfuric acid. Use your nomenclature to figure out that formula there, divided by liters of solution. And I want to just kind of remind you what these numbers are about here. It says that there are 20% sulfuric acid by mass. What that means is that there are 20 grams of sulfuric acid in 100 grams of solution. And why that's important is if we're trying to find something like molarity, like we are here, okay, and we're trying to find liters of solution, we can use grams of solution to find liters of solution, and we can use grams of sulfuric acid to find moles of sulfuric acid. So I just kind of wanted to remind you that when you're starting these problems, giving yourself an equation for what you're trying to find and then writing out the units that you have can help you make those connections of where you can get, like how you can calculate between them. The other thing I wanted to remind you about is the density. It says that this solution has this density. And what that means is if the solution is 1.200 grams per milliliter, that's 1.200 grams of solution per milliliter of solution. So just to be very clear about what that density means. So I'm going to change things around on the screen a little bit, just kind of clean it up, and make room to work. All right. So we're trying to get to molarity. So that's moles of sulfuric acid divided by liters of solution. And I have 20 grams of sulfuric acid per 100 grams of solution, and 1.200 grams of solution per milliliter of solution. Now to calculate molarity, you can first calculate moles, then calculate liters, and then do the division to put those two numbers together. And I'll show you how to do that. It's also possible to do it all in one calculation, and I'll show you how to do that afterwards. So to find the moles of sulfuric acid, I'm going to use my mass percent, and I'm going to use this 20 grams of sulfuric acid. To get to moles, I would use the molar mass. The molar mass is 98.10 grams per 1 mole. And so I would get 0.20387 with 3 sig figs moles. Then the second step would be to calculate liters of solution. And I'm going to use the other part of my percent here. So 100 grams of solution. And then I can use my density. So for every 1.200 grams of solution, I have 1 milliliter, and then I can get from milliliters to liters. And when I do that, I get 0.083, and it's like 3 repeating liters. For sig figs, this has 4, so I'm actually going to give myself another sig fig out there. Now when I put these two numbers together, I'm going to take my moles and I'm going to divide it by my liters. 0.20387 moles divided by 0.08333 liters. And I calculated 2.45 molarity. All right, so I calculated my moles, then I calculated my liters, and then I divided them by each other to calculate the molarity. Now I also said that I would show you how to do that in one step, so I thought I'd do that here. Right. So doing it in one step isn't necessarily any easier, other than it's kind of nice to get all the units to cancel out all at once. So to do it all in one step, you do what we started with, which is starting with our mass percent. And what you can do is just do the calculations together. So this is the molar mass. So when I do that calculation, grams cancels out with grams, and I get moles on top, which is what I'm trying to get. So I know I'm on the right track there. But now I need to get from grams of solution to liters of solution. And to do that, we'd say 1.200 grams of solution is 1 milliliter of solution. And then 1,000 milliliters is 1 liter. So we're doing the same conversions, it's just grams of solution cancels out with grams, milliliters of solution cancels out with milliliters, and the units that I'm left with are moles of sulfuric acid on the top, liters of solution on the bottom. That's molarity, and when you do the math, you still get 2.45 molarity. Okay. So it's just different flavors. You're more than welcome to do them kind of one step at a time and then divide, or you can do them the calculation all together. All right, so I've put our answer for molarity up here, The next one that the problem asks for is molality. So we can do the same type of calculation for molality. We're going to write down what units we want. We're going to try and connect it to the units that we have. Remember, molality is moles of sulfuric acid divided by kilograms of solvent, and our solvent here is water. And to solve this, we already have our moles. We calculated that when we were doing molarity. But to find the kilograms of water, I do want to remind you when we were doing that mass percent, we said 20% mass to mass means that there are 20 grams of sulfuric acid in 100 grams of solution. And that 100 grams of solution equals the sulfuric acid plus water. And we know that the sulfuric acid is 20 grams. So if we're careful about how we do this, we would see that if the total solution adds up to be 100 and 20 grams of it is sulfuric acid, that means that the water has to be 80 grams. So we could also write it like this: 20 grams of sulfuric acid, and there's 20 grams of sulfuric acid on the bottom, plus 80 grams of water. That's useful because 80 grams of water can help us calculate kilograms of water. Now, kind of looking back at what the work we did for molarity, we found out that the moles of sulfuric acid was 0.20387 moles. And now I need to find my kilograms of water. I can use my 80 grams of water to do that. So 80 grams of water. There are 1,000 grams in 1 kilogram, and so that's 0.0800 kilograms of water. Now I have my moles, and I can divide it by my kilograms. When I do that, I get 2.55 molality. Okay. So when we were talking about molarity and molality, again, let's compare that to our molarity. Our molarity is 2.45, our molality is 2.55, not that different from each other. Here, it's a pretty concentrated solution of sulfuric acid, so that's why they are different. If it was a less concentrated version, the numbers would be closer to each other, but they're still not that far apart. So I'm going to write my molality up here to just kind of keep track. Now the last concentration that we were asked to find was the mole fraction. So kind of clean things up here. To find the mole fraction, we need to know the moles of sulfuric acid and the moles of water. If the problem doesn't specify mole fraction of what, we need to find the mole fraction of each component of our solution. So we're going to find the mole fraction of sulfuric acid, and we're going to find the mole fraction of water. The good news is, if we can calculate the mole fraction of sulfuric acid, then we can just subtract from 1 to find the mole fraction of water. Remember, mole fraction is going to be moles of sulfuric acid divided by moles of sulfuric acid plus moles of water. And the good news is we already know moles of sulfuric acid. We calculated that when we calculated the molarity. We did our 20 grams divided by our molar mass, and we found that the moles of sulfuric acid was 387 to 3 sig figs. So we have that. So we have this top and part of the bottom. The thing we need to find is the moles of water. But when we reminded ourselves that 20% sulfuric acid means 20 grams on the top and 20 grams on the bottom, and that meant that there were 80 grams of water, we can use that 80 grams to find moles of water. Right, so 80 grams of water. Water's molar mass is 18.02 grams per mole. And so the moles is 439,511. There were a lot of numbers after that, but for sig figs, we only need 3 sig figs because this had 3 sig figs. So again, we're going to use our moles of sulfuric acid for both of these and our moles of water for this. So when we do that, 0.20387 plus 4.43 like that. And when I calculated that, I got the mole fraction as pretty low, 0.0439. So that's my mole fraction of the sulfuric acid. I could do the same type of calculation to find the mole fraction of water. The mole fraction of water would be 4.43. So it's the moles of water on top divided by the total on the bottom. And when I did that, I got 0.956. Or we could have just said that 1 is equal to the mole fraction of sulfuric acid plus the mole fraction of water. And if we know this one and we know this one, we could have just subtracted from 1 to find the water, and we would have gotten the same number. Sometimes when you do that, when you do it this way, as opposed to the subtraction way, you get a different number, but just slightly different because of sig figs. They have the same meaning, it's just because sig figs are different. Sometimes you get something like 0.956 with one and 0.957 with the other. But it's just sig figs due to different sig fig rules, subtraction or division. But here we have our mole fraction of our sulfuric acid, and we have our mole fraction of water. So I'm going to add those to our list here. And those are all the concentrations the problem asked for. So in this video, we practiced calculating concentration. We talked about molarity, we talked about molality, we talked about mass percent, we talked about parts per million and parts per billion. And then we also talked about mole fraction. Now, if you'd like a little bit more practice with these concentrations, in our course pack, there's a page called Concentration Practice. And it has each one of these things except for parts per million and parts per billion. But if you can get to mass percent, we know that it's really easy to get from parts to parts per million and parts per billion. So if you practice these other ones, you should be just fine.